the person for whom that happens is Rally.
That's true. That's also true.
No, it will loading. You should keep some snaps.
You have to wait until he introduces you. Then. Okay.
Welcome everyone to the talk by Anshu Yadhav, who is a postdoc at ISC Austria. Before that, she was a PhD student at IIT Madras, advised by Shweta Agarwal. And she's going to be telling us about cryptography applied to distributed settings. So,
thank you for the introduction and thank you for guiding my job. Am I audible? Okay, I'll try. Okay, so I'm going to talk about my work on building advanced cryptographic primitives in distributed setting. Am I audible now? Yeah. Okay. So before going into the details of the talk, a quick info about myself. So I'm currently a postdoctoral researcher at ISC Austria. I did my PhD from IIT Madras, guided by Professor Shweta. I have MS by Research from IIT Bombay and MTech from DISCT Gandhinagar. I did my undergrad from Uttar Pradesh Technical University. My areas of interest is theoretical cryptography. So, okay, so coming back to the problem and motivation for the problem. So,
we is also from my city.
Oh, you get the term language. Yeah, that's. Well, you have to just click on the slide. Yeah.
Yeah, so we know that in past years, there is huge advancement in digital technology that generates lots of data, which is very important, that facilitates multiple research, like in AI, medical research and all. And the data is so important that it has been given a different analogy and it has been compared with water, meaning it is priceless. But data is under attack, and if we do a simple Google search, we can find a bunch of links citing data breach. And what we look for is cryptographic solutions to protect the data. And when we think of cryptography, the terms that comes to our mind are like encryption and signatures, like a standard public key encryption, for example. While these are bare minimum requirements, we need more advanced notions of these primitives to address more advanced problems. So, for example, I want to provide, let's say, a fine-grained access control so that I encrypt my data and put it at some place and allow someone who wants to access the data controlled access so that only a part of data is accessible. Similarly, when we think of now who is in control of data, we may want to distribute this authority among multiple parties so that there is no single point of security failure. Now, good, but there is more to it, like how is data generated? So data is generally generated in a distributed fashion. And therefore, for example, we think of this girl who visits different institutions like banking, e-cards, like shopping, traveling, and everywhere data related to this certain same person is generated. And therefore, to protect data in a distributed setting, we need cryptography in distributed setting. So in this, motivated by this problem, I have worked on different problems related in the distributed setting. So one area that I have worked in is fine-grained access control in multi-input setting. Fine-grained is something that I talked about, is providing controlled access to only a part of data that defines your need. And now this in a multi-input setting where the data that is encrypted is coming from multiple sources. In this setting, we defined this notion called multi-input ABE. I will talk about this in detail in the coming slides and give different constructions. Another area is something called broadcast encryption, where suppose I want to send same data to a set of receivers that I can decide at the time of encryption itself. And I want to send my data over a public channel so that, and therefore I would need to perform use some form of encryption. Moreover, if some of the legitimate parties who are, so Of course, like when I'm sending data that is only accessible to by a set of parties, they are having some secret that lets them decrypt the encrypted data. If they misuse their secret, so for example, they come up with some decoder box and sell it illegally or something, there should be a way to catch the culprits. So we have, I have worked on this area as well, and another area is threshold cryptography, which is a wide area in itself. Basically, threshold cryptography means we want to distribute a secret amongst a bunch of, let's say, n parties, so that there is no single point of security failure, and then at least some threshold T of them should come together to compute a meaningful computation. In this domain, I have worked mostly on threshold signatures, where we improved constructions, existing constructions, both from security aspect as well as performance aspect.
What is this code?
Sorry, what?
Code.
This was core confidence.
Yeah.
There is one.
If you did not find out.
For confidence ranking that ranks.
There's an official ranking called code.
Generally,
Australia, like there's an Australian.
use that as.
There's an Australian. That was what I was.
Yes.
Oh, okay.
Yeah.
And FE is functional.
Another area problem that I have worked on is blind signature. So when we think of simple or standard digital signature scheme, there is a message, there is a signer. The signer uses its secret signing key to sign the message, but the message is not hidden. What if I want signature on my message without actually revealing what my message is? And a very good application for this setting is electronic voting. So I, as a voter, needs my vote to be authenticated by some election authority to be counted. But at the same time, I do not want to reveal who I have voted for. So my vote can be my message, and the election authority needs to sign it. In this set, so this is blind signature where the message is blinded. Again, in this problem, we worked on building first overall practical in terms of communication and the signature sizes.
I don't think I follow. So what is sent to the authority in that case?
Hidden message.
Oh,
So think of sending your sorry, a letter in a physical sense, like you have some message and sending it in a carbon envelope.
like it could be the encryption of the message by
It can.
this thing that is
Yeah,
signed by.
yeah.
I see.
And then the signer should sign on this hidden message and send it back to the user, and the user should be able to recover the signature message. Then during postdoc, I continued on extensions of these problems. So in case of multi-input finite access control, again, here I have worked on a more general model of computation. So our previous result works with circuit model of computation. So recall that I said that we want to provide fine-grained access control. What it means is that I want to provide a key that lets you decrypt certain set of messages. How do you define it? We define this through some policy, which can be function. So how can we represent this function? This can be either a circuit model of computation, but that has its own limitations. That if you, for example, if we have to perform addition on different length of inputs, we will need a complete different instantiations. For uniform model of computation, just one scheme may work. So we extend the construction to that. This work is under submission. Another is again in threshold signature. We further improve the existing construction of a lattice-based threshold signature scheme from security perspective. Another work that I have done is working on assumptions. So there was a recently introduced lattice-based assumption called evasive LWE. It is a powerful assumption in the sense that it allowed the community to build certain or many cryptographic primitives that were not known before from simpler tools. And we worked on, in this domain, we found certain counter examples for some contract cases. We suggested fixes and also strengthened the assumption for building more stronger primitives.
So what is the guarantee that the assumption is any good?
Most of the assumptions are like conjecture, and if they stand the test of time,
Yeah,
but-
it's very recent, so it doesn't stand the test of time.
yeah, it does not. So
No, even for LWE, why do you think that would be good?
that I would say has faced the test of time because this has reduction to lattice-based problems, which are long problems. Are conjecture to like hard problems in analysis.
But not USA relevant.
In fact,
The evidence is much weaker. Yes.
yeah, but this is how we come up with new assumptions, and it's both ways. Then cryptanalysts will do cryptanalysis, and if we are not able to break it, slowly and slowly we break it. And or we refine the assumption if we choose. And I continue like there I have working on problems in this area again. So for example, there are other various variants of multi-input ABE that I am working on. Threshold cryptography, I have so far mostly worked with signatures, but in principle we can think of thresholdizing any cryptographic primitive. So that is another area that I am looking for to find solutions to. And assumptions, there are other new assumptions, and the goal is to study those assumptions from both the perspective, finding new applications to these assumptions as well as analyzing these assumptions.
In mining, what is threshold cryptography?
Sorry.
What is threshold cryptography?
So here the secret, whatever the secret, so for example, think of signature scheme, then signing key is the secret. I want to distribute this amongst n parties so that at least 50 T is a fixed parameter of them need to come together and to together doesn't necessarily mean that they need to interact, but they need to contribute in computing. So in this talk, I will talk about my work in multi-input attribute-based encryption. And predicate encryption, okay, I'm using the short forms here, but PE stands for predicate encryption, which is a stronger form of attribute-based encryption. I'll talk about this. So, and if time permits, I will briefly talk about my research efforts. Okay, so let's look at what is attribute-based encryption. So let's think of a hospital setup. Their patients visit and lots of their medical data is generated by the hospital, and this is very useful for medical research, for example, but this should be protected, highly sensitive data. So what we need is to provide a secure storage and access to patients' records. So for example, think of a researcher who wants to study, let's say, correlation between lung cancer and asthma in male patients. So for this, she will need access to records of patients who fall in this category. So she will need to ask the hospital authority to get records of such patients. So what can we do? Can we use standard or basic public key encryption scheme? If we use that, this is a possible approach. That now what the hospital authority can do, it generates encryption and decryption key pair for public key encryption, and use the encryption key to encrypt the records of patients. And now once it is encrypted, it is secure and it can be placed in a publicly accessible cloud. But then the question is, how will we provide access to these encrypted records to the researcher? So we will need to provide a decryption key. But the question is, here there is just one decryption key, DK. And if we provide this decryption key to the researcher, it will provide an uncontrolled access to the researcher. Basically, she will be able to decrypt the records of patients who are outside her study area. And instead, what we want is, okay, so another option can be, whenever such a request comes, the hospital authority downloads all the encrypted text again, decrypt them because the hospital authority has the decryption key, and re-encrypt only the part of data that is needed. So that, and then re-encrypt it now using a different key which can be provided to the researcher. This will work, but this is highly inefficient because we will need to do this decryption, re-encryption. And suppose then there is another researcher, we will need to repeat the same. Instead, what we want is to provide a restricted key that decrypts only the relevant data. So we want to encrypt once, and now whenever there is different requests coming in, we want to generate a different. This is precisely what is attribute-based encryption. So here what happens now, instead of decryption key, it is now some sort of master secret key. And the requirement of the researchers, so for example, this requirement can be defined by this circuit, like a patient who has asthma, who has lung cancer, and is male. We can provide a key for this specific functionality.
Should be all right. As no or like that.
No, because the demand is that correlation in
To
patients
study
having both.
correlation, you need
The full game.
Otherwise, the correlation
All
will
the.
Okay.
Okay.
So that it.
But it doesn't matter for your thing, it's just a small circuit is all that is required. It's not that all gates have to be the same.
In general, okay, so this is an example where I have just shown it by a small circuit. But when we look at it, abstract it out, then we may want to support any arbitrary circuit. That is like in principle. Yeah, the question can be different, maybe, okay. The requirement was I want to access patients in this set. Okay, and now when now the key is defined with respect to this function, and the inputs are this property. So clearly there should be some such information encoded in the ciphertext. So ciphertext, like now the records are encrypted with respect to attributes. So now the attributes can be the gender, the age. Registration ID can also be one attribute based on how we define the system. In respect to this case, the medical condition of the patient can be attribute. And the actual message can be the whole treatment plan, the test reports, the response to the treatment, etc. Yeah, so in this setting,
Make sure I understand. So if I were to think of the hospital record as one large table with a bunch of fields, you want to use this attribute circuit to sort of say what sort of filter to apply on this
Yes.
thing, and then get only those records.
that satisfy this condition. So in attribute-based encryption, now we are I'm saying that we encrypt the message with respect to an attribute. Message needs to be hidden, that is understood. In attribute-based encryption, the attributes are not hidden. So even if I have a key that does not allow me to decrypt ciphertext, I will still get to know what are the attributes corresponding to the ciphertext. If we want to hide the attributes as well, then there is a stronger notion called predicate encryption, where the ciphertext hide the attributes as well. If you don't have a decryption.
I don't understand. So you have some lines in the table where let's say the circuit is false.
Yeah.
Would you know more than the fact that the circuit is false?
I will know that this, for example, row corresponds to some patient. I will go by this circuit itself.
Yeah.
Corresponds to some patient who has maybe asthma but do not have lung cancer. Maybe is a female. But beyond that, I will not know it.
So just the fact that the circuit is false, that's all you know.
No, you might know the 3 specific fields.
What is the reason why it is false?
Oh, I see.
That aspect. But
But
then,
you won't know what their treatment plan, etc.
Yeah.
I see. So for everyone, you reveal these 3 fields.
Yeah.
yeah.
How should we think of the asymptotic solution? So the entire record is n, that's equivalent n, that's something that's growing.
Yeah.
The number of attributes should we think of it as a constant? Is that also growing? How is it growing compared to?
It can be polynomial. It's a fixed polynomial if we are thinking of a circuit model of computation, but number of attributes.
It's polynomial and
Security parameters. So we define everything in terms of security parameters.
and the length of the record is super polynomial.
Length of like the number of
The message here.
the message here. Okay.
What security parameter?
N is the security.
Okay.
Okay. Message here is a bit message. So either 0 or 1, but then you can think of the overall message is basically a concatenation of bits. You can perform encryption bitwise. So
So the number of this is table, so the number of columns
is the question about the number of rows or the size of a message? Because these are two
Sorry,
different.
message is not the, I didn't want to use that, but yeah, I mean the size of the record.
The table.
The entire database that you're encrypting.
That is the number of ciphertexts, so you can, like, any PSP cannot go beyond polynomial. So any unbounded polynomial.
So I think maybe what you asked me that
Basically, the number of patients who have this agenda.
there is no limit on that. It can.
It is not.
Yeah.
But
But is the total length of that record and total number of patients, let's say, is that and the number of attributes, are they of the same order or should we have the number of attributes are being much smaller than one?
number of attributes can be much smaller. In fact, will be much smaller.
Much smaller.
And is there any
Basically, we
attributes
should
like
exploit any relation between. It's just that, yeah.
So there are two independent parameters, security parameter and the cipher parameters. Or are they polynomially related to each other?
Security parameter, just think of that parameter. Everything else can be polynomial. So size of the database, if you are talking about the number of patients, we do not put any bound on that. As long as it is polynomial, it is good, and yeah, that's all.
so it has to be polynomial.
Unbounded polynomial, but anyways, in reality, you cannot go beyond.
No, in the sense that the attribute can be only 10, right, or something. But I
Yeah.
could have but
But I'm
I
not
could
saying
I
polynomial.
want to
I'm not saying
Security
polynomial.
parameters.
Polynomial and security parameter.
Polynomial.
polynomial and security.
Yes. Yes, attribute can be constant, fine. Like if you allow polynomial, that is better, and we support that. But if you want to fix it, fix it. That's it.
So is the encryption going to happen per row or is it something where you take the entire database and per row?
When you say a message, you mean a single patient?
Record details about single patient in the system. Shall I move?
Wait, so I want to know, instead of doing per row, wouldn't it be better to do it per column and then you can just reveal the columns about asthma, cancer, and maybe?
But at the time of inscription, you don't know all. That is one quick answer I will give you.
So you
Like
don't
first-
have a fixed set of attributes?
No,
But you don't know the all the patients that this
First you get to know all the
And
exactly
when
all the
you
parents.
get
That's
with
what
that,
she said. that-
No, but that's no, but that's not so not it's not the all.
but you are thinking with respect to one particular this case, and it makes sense for us to reveal the entire column, but no, again, not entire column.
But I thought you said that even if a row does not satisfy this circuit, you reveal the 3 coordinates.
Only the coordinates.
Yeah, which is, you do it for everything, right? So reveal the whole column.
No, not what do you mean by
But
whole
you
column? I mean,
don't
like,
get
as and when a patient comes, you will be encrypting that.
No, but suppose right now I have.
So is the problem about the database being online, or is the problem, is the database fixed? Is it
Service
static?
is fixed, that's it, it's fixed.
Then if you, for every row, if you reveal whether or not that row has asthma, you know the whole column.
Let's say you, yeah, no, but are we going to do that?
No, we don't want to reveal every row,
I-
right? We want to reveal those rows that satisfy the security.
How will you use this information? Whether, okay, you know the row, and you know that first row, third row, fifth row corresponds to some patient who has asthma.
Oh, I mean,
But how
I
will
think-
this information
I
help?
think this is misleading in the sense that you don't want, like, you don't want just this information about male, female, lung cancer, asthma. You actually want to know the whole treatment plan.
So for the rows that satisfy this circuit, you know the
You
whole.
want the
column.
rest of the row.
You want the whole
Exactly.
information.
Okay. Okay, got it.
Maybe the term correlation is confusing, but
that's what-
okay, but
No, I think there are other attributes also that will also be revealed for those rows where it is.
Yes, yes.
So there's some other attributes like treatment plan, which will also be.
Yeah, the case history.
But for the others, it won't be revealed. For where this predicate is.
attribute-based encryption attributes are never there.
Yeah,
So
that's right,
basically,
but-
think of a table which has first.
So those are not attributes, those are like some data which is.
Think of the last column as a very
where the
By the column where.
all the sensitivity types are.
Yeah, so that column remains hidden, the attribute column gets.
Basically like an SQL query concept.
Okay.
Before, it was like a hidden.
Does this answer your question?
Yeah.
Okay, shall I go?
No, but then why can't you just so then what is wrong with like if all the attributes are anyway going to be revealed, then if you just allow the person to run an SQL query on just the part of the database which does not have the sensitive data that selects the rows, and then for only those rows you
Yeah,
decrypt.
so first of all, then you are not using cryptography there.
No, but you're,
What it means,
you're decrypting.
So then for each row, you have a different decryption key or?
No, you decrypt it on offline and send it.
No, but this is not encrypted. No, this is sent encrypted.
Oh, this is sent in.
Only the receiver.
Only the receiver.
are
Okay,
able
okay.
to be able to
So this will be similar to what you were saying earlier that you will re-encrypt using the public key of the receiver.
decrypt and then provide this control access on the entire.
Only on the select.
Yeah, that would require decryption and re-encryption if you again encrypt and send it. What I understood, perhaps you were suggesting is then using query-based mechanism to protect it. That means if somehow the adversary gets access to your data storage, bypass the query filtering.
No, as the data is still encrypted, right? The data is still.
Okay, that's perhaps what you are saying is.
That
I'm using the word perhaps because I might have misunderstood your question. Please correct me if that is the case. But yes, then you will have to decrypt it entirely.
Well, only the rows that are selected.
But even the ones I have encrypted the data,
Well, I think the only one
Or
pair of
even
keys is to
yes.
encrypt the entire database. You don't want to
But it
decrypt.
is-
Oh,
The hospital is
so
going to decrypt the entire database and re-encrypt 5 and all.
yeah.
okay. Okay, I think we
Yeah, let's
go
keep
going.
I think the setting is the key is one single key which is encrypted the entire database.
Yeah.
The master key is one single key which can decrypt the entire database.
But not it's not.
Yeah. But the SK is the specialized key which will only decrypt 5%. And that's generated depending on the attributes.
Yeah. Okay.
If you want to
And
and the second.
Okay, so in predicate encryption, attributes are again also again. Now you will not even get to see the email columns. So here is a formal representation of attribute-based encryption. I will very quickly go through it. So there is a setup algorithm that outputs the encryption key, which we call master public key, and master secret key. Then there is key generation, which takes as input a function. This function is basically the policy that defines what I can access and outputs a secret key F. Then encryption takes the master public key and message and attributes. So as I said, message we consider just a 0-1 thing, but you can encrypt each bit separately. And attribute is bit string. L can be polynomial in the security parameter. It outputs the ciphertext. Then there is a decryption algorithm that takes the ciphertext and the secret key and outputs the message if and only if fx is true. And in security basically says that even if I give you multiple such keys for different functions, if none of them allows you decrypting the message, so basically if all the functions evaluate to false on the input x, then the message must remain. We capture it through this indistinguishability notion. Non-decrypting keys means keys for any function g such that gx is equals to false. And indistinguishability notion basically says that under this situation, basically encryption of M0 is indistinguishable to encryption of M1, computational indistinguishable. In predicate encryption, the attributes are also in it. What it means is now here, earlier it was X same, only the messages were different. Now the attributes are also different, X0, M0, X1. Okay, so coming back to our problem, that the example that we were discussing, there we were making an implicit assumption that when I am encrypting the record of a patient, I know the entire records, like there is a single encryptor who encrypts the records of this patient. While in reality, what may happen that the different departments, like the hospital may have different department treating different diseases. So, for example, there can be an oncology department treating cancer and similarly pulmonary department. And now when the patient visits, so the records of the patient related to cancer is with the oncology department and records for asthma is with pulmonary department. And for the encryption, we wanted the attribute. Now, this information about the attribute is distributed across two departments, and the question is how will we perform encryption? Again, a naive approach can be think of a central repository where each department can send their records, the records of the patient. And this repository then can work as before. It has the encryption key and the master secret key and use the attribute-based encryption in the single key setting. But then the first question that will appear is how will these departments send the records to the central repository? Again, this cannot be sent in plain because for safety reason. And if they are not sent in plain, then what is the other option? That they encrypt their records using the public key of the central repository. And then the central repository decrypts it and re-encrypts it, combines the records from the two departments and re-encrypts it using the predicate encryption or k-ABE. Again, this is inefficient and compulsory. In fact, what we want is that allow these departments to encrypt or partially encrypt, as you can call it, whatever the information that they have. So let the oncology department encrypt just with the information of whether the patient has lung cancer or not. Similarly, the pulmonary department can just encrypt with the partial information. And once these are encrypted, again as before, these encrypted records can be placed on the cloud and provide the key as before. And at the time of decryption, we use these independently generated ciphertexts along with the key that works on attributes coming from both the ciphertexts. And if the, as before, if the combined attributes evaluate to true for the corresponding function, then allow the underlying messages to again, a formal definition for this is there is a setup key. So there is one difference now. Now in multi-input setting, we work with secret key setting where the encryption is also a secret operation.
Sorry, Anshu, can you just go back 1 second?
Yeah.
So for example, over here, so now you have some rows which don't have all the attributes. For example, like the second row will not have the has lung cancer attribute.
No, what I'm saying is there is second row, but neither of the department has information about the entire. And like there are entries, but oncology does not know the entry, let's say in the third column.
That's fine. But like when you do the descriptor, like whenever you compute this g of x or like whenever you want to figure out whether this predicate is true or not, how do you do it if you don't have the full?
No, so I am taking now the two ciphertexts. One coming from the oncology department, another coming from the pulmonary.
So it's like a join of two databases, then an SQL query. Oh, I see. And then decryption.
So on the cloud, we are going to be storing, I don't know, after some combining operation of those two ABE encryption.
No, I'm just in no combination. I
Separate.
store whatever is, you can call it partial ciphertext.
You just stored the entire thing, whatever came from.
So my worry right now is that, like for instance, suppose in the oncology department there was some message involved in this. There is a particular patient who has lung cancer but not asthma. So technically that's a row that I should not have access to.
Yeah.
But what is preventing me from getting access? Because there is an ABE encryption with respect to the oncology department that seems to give me access to that row.
Like
the
functions might be applied on both
First,
sides.
you cannot just take partial ciphertext alone with the key. So your key expects two ciphertexts to come. And now two ciphertext when you take that. So in this example, maybe you can add one more now since there are the ciphertext is coming from two sources. And I think your question is perhaps that what if I take record from one patient who has cancer but not asthma and another patient who has asthma but not cancer and combine these? So you can perform extra check that their IDs should match.
So these checks are performed by whom?
By the circuit. So I can define this circuit now.
It's performed by, like for example, if I am a researcher that is interacting with the cloud, it's performed by the cloud before the data is given to you.
It is so you as a researcher will get a key.
Okay.
That key is corresponding to the function.
Okay.
Now this check is defined in the function itself.
Oh, okay.
So I think the whole point is the whole data will be shared with the researcher, right? And
Data.
Oh, okay.
It is encrypted,
now I
it is there in the cloud. I don't need to worry
Oh, that is-
beyond providing you a control. Right? So yeah, here now we are in a secret key setting, in the sense encryption is also a secret operation. It is inherent actually to multi-input setting. Otherwise, it gives uncontrolled power to the adversary. And now encryption, as now we saw that there are multiple encryptors. So now we label the encryption algorithm with ith encryptor, let's say. So this is like I'm giving this definition for k-ABE. So there will be k encryptors. So each encryptor has a message and attribute, and it gives a partial ciphertext CTI. And the decryption takes k ciphertext, one from each slot, and performs a joint decryption such that the underlying messages is received if f on the underlying attributes evaluates to true.
So the master key is shared across all the encryptors?
Yes. Okay, so again, master secret key can consist of bunch of
So like they
different.
derive it from, they derive their.
Not necessarily derived. It can be anything. I have abstracted it out and put everything in MSK. So, for example, MSK can have a SKG, let's say secret key for key generation, encryption 1, EK1, EK2, EK3 or something. And in that case, maybe encryptor 1 only needs to know N1. Sorry, EK1. But it is still secret key setting because you are not making it public. So, for example, someone outsider who is not the encryptor one cannot.
So then in what way is this picture different from the previous? So you're saying that there's something about.
There are multiple encryptors.
No, that is fine. But you also think there's some other difference about something being secret now that was not secret in the previous.
The encryption algorithm is now using this master secret key.
Oh, the encryption algorithm itself.
Yeah. Previously, it was using master public.
Okay.
So anyone can. Okay. And again, in predicate encryption case, the attributes will be hidden by the ciphertext. There is one simplification we assume, which is again without loss of generality, that the message is associated only with the first slot. So let's or one slot without, again, we can think of first slot, for example. And the rest of the slots, messages slot is kind of empty. They just have attribute. And notice that even though we are saying that we don't hide the attribute, so the question can be, since the other slots do not even have a message to hide, the attribute is anyways known. What is their role? So the role is that, notice that the encryption is now a secret operation. To perform a decryption, you need ciphertext from all the slots. And that is something that adversary cannot do by itself. So even to be able to perform decryption, you will need encryptions from these slots. And then let us look at security definition. So security, intuitively, what it will say that if I give you decryption keys for different functions, the message should remain hidden if these keys do not allow you to decrypt any combination. So this is first a notion of security, where we say that think of an adversary who has two secret keys corresponding to function f1 and f2. Two ciphertexts from slot 1 for m1, m2 and attributes x1, x2. And for slot 2, as I said, slot 2 does not have any message, so it is just x2 and x2. And now what we say that if all, so we can say see that there are 4 possible combinations. So slot 1 first ciphertext combined with any of these 2, and similarly this combined with any of these 2. Total 4 combinations possible. If all these ciphertexts are non-decryptable by any of the 2 keys, so this is what the condition says. If f of x1, x2 is equals to 0 for all possible combinations, then all the underlying messages must remain hidden. Then we define a stronger notion of security, which allows decrypting keys. And what it means is that, for example, in the same setting now, suppose F1 of, so basically this pair is decryptable, suppose. But what about the second one? Suppose any of these 2 pairs are not decryptable. In that case, M2 should remain hidden. This decryption was not allowed in the previous.
So the left side is one encoder, the right side is the other encoder.
Yeah.
And the first one is saying that if what is all possible combinations?
In the previous setting.
Product of the rows.
So you combine the first ciphertext with any of these 2.
Okay.
So this will give you 2 pairs of ciphertexts. And similarly, you can combine this with him. So there are 4 possible
combinations, yeah.
And none of them should be decrypted.
Okay, then both the messages F1 and F2 are secure.
Yeah. But this security notion does not say anything if any of them becomes decrypted.
Okay.
The stronger notion allows that, which now says that even suppose the first combination is decryptable,
Then M2 is.
but if M2 is not, so clearly if this is a satisfying set, M1 cannot be hidden.
Yeah.
But what about M2? So if M2 is something which is non-decryptable because of any combination, then it should be.
Yes.
In this domain, these are our contributions. So we defined the notion of multi-input ABE formally for the first time. This notion was informally introduced in a different context, but no formal definition or any construction was provided. Then we gave 2-input ABE, where there are 2 encryptors now, for from lattice-based assumptions and discrete log-based assumptions pairings for log depth circuits. Then in our later.
The log depth circuit here, the circuit that will take the attributes as input and that
Yeah,
circuit for that function.
Yeah. Then we in our later work we constructed constant input attribute based encryption from lattice based assumptions, both for log depth as well as polynomial circuits. And then for simpler functionality, that's which is basically conjunctions of NC1 that supports polynomial. We also give compiler that given any constant input ABE gives us constant input predicate encryption. So we call predicate encryption is a strong notion of attribute based encryption. And we also gave a compiler in a different work, which if you are given with a constant input ABE for circuits, it gives you that satisfies certain properties that we identified in the work. It gives constant input ABE for uniform order. So this is results from multiple work. So crypto 2020, yeah. And one work.
k-ABE stands for how many different
K is the number of
encryptors.
encryptors. Yeah. Okay, so one question is attribute-based encryption. Okay, I didn't talk about functional encryption at all, and in the interest of time, I am not going to talk about that. But functional encryption is a stronger notion or a generalized notion of attribute-based encryption. And as I said, multi-input attribute-based encryption was not defined before, but multi-input functional encryption was defined. And there were constructions for similar functionalities. And the natural question can be then if we have something for the generalized functionality, it will give us restricted functionality. But since attribute-based encryption is a much simpler functionality, it is always desired to look for a direct construction rather than going through a complex, because functional encryption is even in a single input setting is a much powerful but at the same time very complex.
When you say poly-ABE, it's polynomial security parameter.
Okay, yeah.
And what is the lattice-based assumption?
We use for the second point, it is we use LWE, learning with errors, and recently introduced it is called invasive.
What is the status of LW? Like if you can solve LW, you can solve some ABE problem?
Yeah.
With what parameters? And what approximation parameters?
It will be polynomial again, but I don't remember the exact thing. But
Polygon is the dimension of the lattice.
yes.
I see. And the best algorithms for lattice is what? Sub-exponential kind.
Okay, I don't remember the exact, but there is in lattice problems, there is a trade-off like approximation versus time you take.
Oh.
So if you go for exponential approximation,
Oh.
then you can solve it in polynomial time
Correct.
and vice versa. Polynomial for both is not known, but in between I am not like
So,
updated.
yeah, I'm just wondering if the connection from LW to CEP is stronger than the connection from, let's say, RSA to factory. Because really there is no formal connection between RSA and factory. Except for the trivial one that if you can factor, you can do RSA. And the reverse is not true, right? I mean, if you can crack RSA, there is no proof that you can do factory.
I see. From LWE to lattice problems, there is a connection. I don't know if that matches with the
Yeah, I'm wondering if it goes both ways.
both fields.
There'll be trivial side, there'll be a non-trivial side. Like,
So if you can solve LWE, you can solve lattice problems. But if you can solve lattice problems, can you solve LWE? I'm not sure about that. Perhaps yes, but this is not a.
and is the average case to worst case reduction valid for LW also?
Yes. Yeah. Yeah. So worst case problem in lattice gives you average case hardness.
In LW.
Yes. Yeah, shall we think on? So in this talk, how much time do I have to have? This.
I think there have been a lot of questions, so we should give it 5 or 10 more minutes. At least 20 minutes. Yeah, we have around 20 minutes. Okay.
So okay, in this talk, I will talk at high level again about our construction on two input ABE from pairings and LWEs, and just an outline of k-ABE to k-ABE. So yeah, let's begin with this. So let us first understand what is the main challenge, given if you have a construction for attribute-based encryption in a single input setting, what is so challenging in going to a multi-input setting? So think of a setting where we want to encrypt for an attribute, which is, let's say, 6-bit history. But in multi-input setting, what is happening is that this is now divided across two encryptors. And for encryption, we need to know the attribute. Now, the problem is if any one of them want to encrypt, none of them have complete information about what the attribute is. So what can we do? So the natural approach is to at least look at how does the encryption schemes for attribute-based encryption in single input setting look like. So a scheme by Bonnet and the co-authors based on LWE is something that is helpful for us. It has nice properties that can be exploited in multi-input setting. So one very nice property about this scheme is decomposability. And what it means is that suppose I have to perform an encryption with respect to an attribute, just for simplicity, I'm thinking of a 4-length attribute here. What it does is, so 4-length attribute at each position, it can be 0 or 1. So what it does, it encodes 0 and 1 for each position. And let's call these encodings as by C and indexed with year, position and bit. And then when for an actual, okay, so these components or these encodings look like this, something like this. So the main thing here that will be useful for the coming slides is it has a secret vector S, which is common because this is not indexed by I or P. But there is a matrix M which is indexed with ID, means this depends on the bit position and the bit value. Has to be common for all the encodings and plus some noise. Noise and secret, they both must be hidden. And so now with this, what happens that now to perform and to give out a ciphertext for some attribute, for example 1011, what we do is select the corresponding encodings, give them out, and the rest of them must be hidden. So we simply don't give them off. Now, how is this useful for us? At least this lets us make some progress, because now what we can do is tell the first encryptor to compute the encodings for its own bits, and similarly the second encryptor can compute the encodings for its own bits. So we have made some progress, but we will have challenges.
So the first encryptor has the first part of the secret, and second encryptor second part of the
Attribute bit. Oh, not the secret. So if you are talking of the secret, yes, no, they don't have. They do. The encryptors have the attribute only.
Okay.
In fact, the requirement to use a common secret is a part of the challenge that we work.
Okay, so I mean, but right now, then both the parties have known the identity of this. Is that right?
No, so they don't know S.
Ah.
S is something that should be fresh. So, like for each ciphertext, S should be different.
Oh.
They're only given the CID for the corresponding I.
Those CIP, that is something they will
No,
compute.
so then how does this compute separately? So if they don't know S,
We will address that. In fact, that is the next.
What is the difference between the secret and the noise thing?
Noise is also secret. Noise is low now. Secret can be from a random from ZQ space. Sizes are
So for a fixed secret, you have a probability distribution for the noise bit.
no, noise is independent, secret is independent. They are not correlated.
So just to make sure I understand this thing, so the MIBs are all public information. So had the encryptors known what this common secret would have been,
Yeah.
they could have computed the corresponding CS.
Yeah. And
The- Okay, the issue is just that they may not have access to this common.
yes.
Oh, okay.
But it's still, it lets us at least this nice decomposability property at least gives us some step forward, that at least in terms of, so basically our problem has reduced to just ensuring that there is a common secret. And in fact, that is what the next set of challenges is. That okay, there is some decomposability property. We have seen that okay, they can divide the task. But then the question is that these two ciphertext components are generated independently. And these ciphertexts must be combined in a way that decryption is possible. So basically, they need common secret. And the first bullet, by definition, it means that they cannot end up using a common secret because they are working independently. So the question is, how do we make sure that there is a common randomness? For this one, first attempt can we make the secret part of master secret key, since both the parties are using the same master secret key. But for security, we need fresh randomness for each ciphertext. So this cannot be shared a priori. So here we make use of pairings, and we'll see how it helps us. So a quick refresher on pairings, but should I go over it or can I skip it? Okay. Okay. So we know discrete log problem, right? So there is a group of a huge large prime order, and any element, let's say rank A, can be represented as d raised to power A. And discrete logarithm tells that given this capital A, if it is random, you cannot find a small a. So in some sense, it encodes this small a. Right? What is computational Diffie-Hellman problem? It says that if I give you capital A and capital B, again random, encoding small a and small b, you cannot compute g raised to power ab. So basically, you cannot perform any multiplication in the exponent. Pairings is something that allows you to do that. So pairings is basically a map which takes two group elements as input. These groups can be same or different. So here this is for different groups. And first is encoding A, second element is encoding, let's say, B. The map gives you encoding of AB in the target. So it basically allows you one multiplication, but you cannot go further. So now if you want to perform second multiplication, we can do that. And in the rest of the talk, I will use a notation for basically this notation. So Z represents the group. So here we have three groups, 1, 2, 3. And bracket A means group generator raised to power that way. So how is pairing helpful to us is now what we can do is first encryptor can have a fresh randomness T1 at the time of the encryption and code it in G1. Similarly, second encryptor has P2 and encode it in G2. And when we pair them, we get encoding of T1, T2, and both the encryptors will get encoding of T1, T2 in the target. So basically with this approach, what it will look like is now what we can do, in the setting, we know the length of the attribute a priori. So maybe we can make these ciphertext components part of MSK, computed with some secret S. But as we saw that we cannot reuse the same secret again and again. So whenever I have to compute a fresh ciphertext, I will re-randomize it. So basically, for example, if encryptor 1 has to encrypt for attribute 101, it will select the corresponding encodings, re-randomize them with T1, encode everything in the exponent of group G1 and give it out. And similarly for encryptor 2. And now we can pair them up. After pairing, what we get is these components with fresh randomness T1, T2 for all the 6 positions. But these are encoded in the target. Yeah.
Right. We didn't follow some. So you said given if you know G to the A and G to the B, then it's expected that it's hard to do G to the AB.
Yes, if you do not have pairings.
Now, how is pairing? What is pairing? It's just an algorithm, it's just this.
Yeah, now it takes 2 group elements. They can be from different groups. You basically need encoding. Now, these encodings can be in different groups as well, but it allows you to perform multiplication of the encoded things. The structure of the encoding is perhaps changing. In fact, here it is changing. You had encoding in group 1 and encoding in group 2. What you get is encoding of the multiplication, but in a different group. It's basically target.
I see. Okay, so the hard part was maybe getting an encoding in the same group, but you bypass that?
No, basically the hard part was getting an encoding of multiplication, which we can do using pairings.
But I don't understand how can pairings be possible if the Diffie-Hellman is?
So in that group, Diffie-Hellman would be.
Oh, I see. There's a quantifier on group or Diffie-Hellman.
Just think of the bracket as just being some way of encoding T1. So it just says if you have a way of encoding T1 according to group 1, T2 according to group 2, you can get the encoding of T1, T2 according to the third group.
Yeah.
And this is not taking computation Diffie-Hellman.
Because I haven't told you what group, what the encoding is, nothing.
Okay.
I mean, this is an abstract statement.
Yes.
Thank you.
Okay. So once we are here, so basically we have got what we wanted, but there are a few hurdles still. but we are closer to the solution. So does this work? We need to perform 2 checks. Is it secure? Is it giving us the functionality? So at the level of security itself, we observe that this scheme works, but in the stronger security notion, where recall that we were saying that we allow decrypting keys. This scheme will have problem. In particular, this is the issue. That now think of an adversary who has one function, one secret key for some function f, 2 ciphertexts for slot 1, and 1 ciphertext for slot 2. And suppose this combination is decryptable. Once it is decryptable, there is no guarantee left on the secrecy of the errors terms involved. So recall that the encoding had some noise term into it. That must be kept safe. But once you perform a valid decryption, this noise too is not guaranteed to remain safe. And once that leak is leaked, specifically the noise.
This would also happen for single input, right?
In which?
For the single input case.
But this is when you are allowed to perform a decryption. So even in a single input case, the noise is revealed, but this noise is fresh each time. So even in a single input case, yes, you have a ciphertext. You could perform a decryption using the key, but if you could perform a decryption, there is nothing left to hide.
Okay.
And for the next ciphertext, there will be a new noise.
I see. And here because you're parenting, you're reusing the noise.
No, here, and I will talk about the problem soon. So here, actually what is happening is this pair. CTX2 is reused. So because of the blue combination, this was a valid combination. The adversary could perform a decryption. Therefore, the noise in CTX2 can get leaked. But because of this leakage, this red combination becomes strong. And to handle this, what we say that instead of making these encodings part of master secret key, we let the encryptor 1 itself compute these encodings on the fly. So whenever, for example, it gets its attribute 101, it computes the encodings with whatever, it chooses fresh S, fresh noise, computes these encodings as T1 with it. But for the next 3 values, which are coming from the user 2 or encryptor 2, it does not know what these values are going to be, so it will have to provide the encoding for both possibilities at each position. Right? And these are encoded in the exponent so that the adversary will not get to see them as such. Whatever it gets is in the exponent. And what does user 2 do? User 2, it simply provides selector bits. So for example, if its attribute is 100, it chooses its fresh randomness and provides its encoding in group 2 for the corresponding positions. And for the decryption, what we can do is, we can pair the matching positions. And when we pair the matching positions, so for example, if this is paired, again we get what we want. And for example, if we pair this and this, the adversary will get 0, basically no information. In fact, we don't want to provide something like this. So this seems to be working, and in fact, we are quite close to the solution, but there is one more problem left. That we observe that for every position, these are tokens. So nothing prevents the adversary from from pairing non-matching positions. Right? So for example, the adversary can map these 2 positions and recovers an encoding for C51, basically refresh. What it means is that the adversary has got an encoding for bit value 1 for this, which is actually 0. And this is problematic. So for this, what we do, we introduce pairwise, position-wise randomness. So now in this, we also have these W values. So user 1 or encryptor 1 uses these W values in the numerator. And notice that here also this is different for 0 and bit 1. And user 2 uses them in denominator. And these are made part of master secret key so that both the encryptors know. And now when we map matching position, they will cancel out nicely and we get what we wanted. But now if we take map non-matching position, they won't cancel out and what we get is some. randomness. And now we can actually formally prove that this is secure. But then the question is about decryption. So notice that so far we have managed to get the BGG plus encodings with fresh randomness, but everything is in the exponent of the target. And this is just the ciphertext component. We still need to perform decryption. And since the things are in the exponent, we will need to perform decryption operation somehow in the exponent. So yeah, this is what we have so far. So for that, and since we are already in the target group, we have used the power of pairing to perform one multiplication. We are already in the target group. We cannot do complex operation in the exponent. But then again, the question is, let us look at what the BGG plus decryption looks like. So BGG plus decryption is a two-step process. The first step is a linear operation, which basically gives us a noisy version of the message. And then the second step is rounding operation, which removes the noise and gives us the message. Corresponding to this, what we have is ciphertext components again, but in the exponent. But in the exponent, we can perform any linear operations, right? So for example, given encoding of A and B, we can multiply and get encoding of A plus B. So till this step, we can work, and what we will get is noisy version of the message, but in the exponent of the target group. And next step, we are stuck because rounding is not a linear operation. So here what we observe there is that if this noise is small, in the sense that if we can bound it by some polynomial, we can use brute force technique. In particular, observe that since the message is just either 0 or 1, if message is 0, what we get is just noise in the target group. Otherwise, some large value plus noise in the target group. So what we can do, since it is guaranteed that noise is small, I can try every possible value for noise, starting from 0 up to B. If any of them matches with what I have received here, if any of them matches, then I know that I am in M is equals to 0. If not, then I can output M is equals to 1. But then the question is, what is the guarantee that noise is bounded? So this is guaranteed if my circuit for which I am providing the key is a locked circuit. In fact, the restriction of NC1 comes from there. This work was in crypto. So I want to mention that the techniques that we use here were developed in a previous work by Agarwal and Yamada in a different context. But it was surprising to us that we could use similar techniques in a completely different setting of multi-input APE.
So for the decryption process, what are the keys that the decryptor will need? Does the decryptor need the master secret key for it?
No, it will use SKF.
Oh,
the key
only
for
SKF.
the function F.
Okay.
Yeah, and will perform the BGG plus decryption. I will just quickly, though the main technical part is done. So this is limited to array 2 because pairings allow us to perform only one multiplication. So for example, if I had to go to array 3, I needed something like this. Multiplication of T1, T2, T3 in the target group, which is not allowed by pairings. In our later work, we constructed constant input ABE. This is a very different construction, so I will not talk about the construction. Just a small observation about, or a note about this work. Yeah, it was based on a new assumption of evasive LWE and tensor LWE. So basically, at a very high level, something that we got from pairings, basically generating common randomness. Same effect or similar effect is achieved by tensoring between two vectors. And tensoring does not have any limitation that you can do only 2 or something like that. In particular, so it can be applied as many times as you need. But what about, so we can do this for 3, we can go on. What about the sizes? So the common randomness is tensoring of those many vectors. But the size is lower. So, for example, R1 tensored with R2 will have size L is square if L is the length of this R. And after constant, so for example, so basically, after k tensors, we will have the size of the randomness raised to power k. If k is beyond constant, it will become super polynomial, which is decryption. That's why we restrict to constant. Okay. So this is just a result about, again, I will not go into the construction aspect, just what we achieved. So to go from ABE to 2ABE, we used LW and pairings, and the natural question is, can we use existing construction of predicate encryption?
Maybe this is probably stupid, but if you go back one slide.
Yeah.
If you have k inputs, then your complexity is growing polynomially, right? Goes in the exponent. If k, even if k is constant.
K is constant.
Yeah, then it becomes something that has k in the exponent.
Sorry, can you repeat?
The complexity of encoding, the complexity of doing this procedure is something that has k in the exponent.
No, it is, so basically lambda raised to power k something. Right?
Yeah, so yeah.
So, but if k is constant, it is still polynomial.
Yeah, that's not where I'm going. So I was saying that in the motivation, you said that if you have these different departments that are all sending
Yeah.
it, then you'll have to encrypt it and decrypt it independently.
Yeah.
That would have k that is multiplied, it would not be in the exponent. So that would be more efficient, right?
But that also depends on how many users you want to support. Suppose the same number of users keep coming, and you will have to repeat the same process again and again.
Wait, what do you mean? So you have k different departments. They encode their data using a public key.
Yeah.
They send it to the common thing. He decodes and then he computes the encode on its own. Now this reduces it to one input with k that is multiplied and not in the exponent.
Yes.
So the constant factors are different. In this case, you will decode the whole data. Encode and decode and encode the whole data. In this case, this k is happening like this. The thing that is in the base is something, some constant.
I don't think.
Let's think of k is 10.
Yeah.
So lambda raised to power 10 is the
So you had
size of
you had a section that was what is lambda here?
some security parameter. It is few hundreds of bits.
So it's something that is poly in the length of the database,
It is independent.
but the
But
database is
whether
already
it's the
one
length
input.
of the database can be poly.
Okay.
And all the indistinguishability will be indistinguishable up to 1 over polynomial. The rest.
I don't immediately see why this is more efficient than just doing k public key encryption. But I think that-
Let's about k equal to 2 or 3 or 5 or something like for small enough k.
Why?
Actually, I don't see what is the solution, what is the other thing, I mean, like.
So you have k different inputs.
No, you think you have to encrypt and decrypt the entire database. at
K
party
times.
one. Yeah, at party. But here I think they're not doing that.
They're doing it once.
But
Yes.
once is just the one.
But
Not it's independent of the number of
But
people.
there's a different parameter.
Yeah, but then
This is something that's done by the researcher, not by the hospital. I mean, if you want someone to decrypt and re-encrypt, you're asking the hospital.
So there is now a new dependence on the number of users.
Yeah.
In the here is not.
Not clear, but let's take it out.
so the question could be, can we use the similar approach to build multi-input predicate encryption from existing constructions of predicate encryption? But we use certain properties about the attribute-based encryption. So for example, noise growth must be limited to polynomial. And we don't know predicate encryption in single input setting that satisfies this property. So we take an alternate approach, and the alternate approach is this. So there existed a construction or a compiler rather that converts an attribute-based encryption to predicate encryption using some tool called lockable obfuscation. Basically, that can be built from LW. Okay. So we take this route. We then build a compiler that takes. So we can go from ABE to multi-input ABE and then go from multi-input ABE to multi-input PE. And we build this compiler again using lockable obfuscation. But again, since we are in a multi-input setting, the problem becomes much more complex. And in fact, our compiler works for any constant entity. Using this combined, the results that we get for ABE, we can lift it to predicate. And this is the result about uniform models of computation. Future plans, these areas of multi-input crime access control has multi dimensions to it and interesting problems, questions therein. So, for example, questions about assumptions. So, like assumptions, classical assumptions versus post-quantum secure assumptions. Then the question can be standard assumption, which in which we have much more faith, which are there for long. The versus stronger assumptions, which are recently introduced, and improvements in that domain, or there can be trade-off. Then security. So when we talk of adversary, and the adversary can ask queries about ciphertext. So since the encryption is in a secret setting, to get the ciphertext also, the adversary will have to issue queries. The adversary issues queries related to keys. And then the question is, when does the adversary make these choices? So in the natural notion, we should allow the adversary to make this choice whenever it wants to in the entire game. But this is adaptive notion of security, which is hard to achieve. So we work with selective notion of security, where all the choices are to be made right in the beginning. Then the questions are, can we achieve any notion of adaptivity there? Then the other question is about functionality. How complex function can you support? Then what form of computation, what model of computation can be supported? Arity, poly, constant, etc. Trustless system is another interesting direction. So we are talking of key generators. So there is a key generator who has this master secret key, and if I need a key for my function, I have to go to this key generator. So we are placing our whole trust on this key generator. The question is, can we get rid of such a key? And what it means is that maybe when the different users with different functions come up with their own secret key and go to a key curator, which we call it as, which will aggregate all these keys to give a master public key. So, and this curation is a thing which is publicly verifiable, so this cannot cheat. And we get rid of any party who has any secret with it. This is an area which comes under registered setting, and yeah, so when we do something like that. Then other variants are there. So for example, multi-client variant basically adds one more parameter to the encryption called label. And the ciphertext can be combined only if the labels match. And what interesting questions can be asked or there. Then improving parameters. Another area is threshold cryptography. Again, some common questions are related to security, trust level, parameters, assumptions, but questions specific to threshold cryptography is, for example, when we say that at least P parties need to contribute to perform some computation, do we allow interaction between them? So the best setting is non-interactive setting. But if we if we allow interaction, can we achieve something more? And again, dealing with the trade-offs there. Thresholdizing any other like advanced primitives. So for example, can we thinking of thresholdizing multi-input ABE where let's say key generation is thresholdized, questions like that. Even in threshold signatures, there are questions related to improving the security and all. In long-term plan, I want to work into quantum cryptography, though I've done coursework on this, I have attended talks. So far, I have not worked on any problem building cryptography from quantum computing, but this is thing that interests me. Also, from post-quantum assumptions, I have worked with lattice-based assumptions, but there are other post-quantum assumptions as well. For example, isogen. I want to and that area interests me, and I want to get into that as well. Other activities is like building a strong research group, getting grant proposals and actions. These are my publications. And So these are the courses that I can teach basically. And in cryptography, so I could find those courses. Title is a bit different, I think. Perhaps a course on cryptography from lattices is there. So post-quantum cryptography, something, and foundations of.
What is the called postcode?
Sorry.
Why is lattice-based cryptography called postcode?
Because lattice-based assumptions are supposed to be.
Why?
That is conjecture because there are attempts being made and we.
There was a very serious attempt a couple of years back.
Yeah, but that turned out to be false.
Yeah, that's one attempt. So really, I mean, there is no, I mean.
No, but because the failed attempts do not get cited because they don't come, but there are groups of people who are trying to make this assumptions.
NIST seems to think that lattice-based vectors are.
Yeah, but I mean, at least factoring all that has a huge pedigree. The discrete law.
But factoring is broken by quantum. Okay.
Yeah, I'm just talking the analogous thing. I mean, not many people in the quantum community probably have tried those problems.
I think these problems are tried, and my understanding is that basically what I said, the failed attempts do not get counted for. But yeah, I think there is a serious effort being made to take these assumptions. And yeah, would like to do courses on quantum cryptography where we study quantum algorithms and also building cryptography using powers of quantum computing. And advanced topics in cryptography which will contain topics related to homomorphic encryption and function encryption and etc. I have worked as teaching assistant for various courses in theoretical computer science at IIT Madras, and these are my awards. Thank you.
Regarding Pranav's question, is the entry hardness of the shortest of the problem not good enough?
Well, usually you will not want it to be anything hard. I think, right.
Okay, well.
You want to get it intermediate. So
Yeah, sure, but when it comes to is the assumption do we expect it to be secure with quantum computation? Would that be something?
Actually, I don't know, like, what would satisfy?
Yeah, but would that be the answer to that question?
That's what, I mean, other than some people have tried and failed.
That is, I would say that all the assumptions of cryptography, that I think is based on shit. The standard test, like that, people have tried.
Yeah, but the question is what we know about the structural complexity of CV. I mean, factoring we know is
Yeah,
is
so
the intersection point, right? So what do we know about CV? There are some analogous methods, I know that. So with square root and approximation factors, it's an intersection point.
with
CVP. Huh?
with CVP, I am not that familiar with the cryptographic or the algorithmic aspect of those problems.
Yeah, I mean, there are similar things. Less is known in structural complexity of CV, but some things are.
Because of time, maybe everything and quality, one number people were maybe around the same time. There, around. But again, they're not conscious. Typically, the best algorithms are in vintage.
Yeah, well, I mean, I think much more work has been done than
I would say again.
No, the quantum hardening is supposed to be or something is wrong. It's not that much. What you
I can't say much about that. Also, one thing I have
some smart person like Shubho may come in k-ary. It was a big scare, right?
That one was the story.
And that was a very serious
it's more positive.
It's not the first attempt.
It failed, and that's a good news for us.
Yeah.
Yeah.
Yeah, but the thing is, I think probably in the case of factoring, there have been many attempts at that caliber of case.
I don't know what that means. I mean, I mean, like LWE has been around for a fairly long time now.
Oh, 20 years?
I mean, in fact, when the number theory came, factoring was not around for more than 20 years.
I would say
Yeah,
it's not about
But yeah, I agree.
LWE with proof reduction to latest problems. So we should not think about LWE, we should think about LWE problems and which are there even reasons.
No, the thing is, before LWE,
Let me say stop the.
lattice problems as a base for public cryptography have been proposed from right? Yeah. Now the question is the quantum. That's not.